You hear about a comet, 3I Atlas, interstellar visitor, alien rock. Headlines call it mysterious, social media says it could be a spacecraft. Astrophysicists debate on cable news, but most of what you hear is noise. The real story sits in the data, the measurements, the numbers that came back from telescopes in Chile and Hawaii in space. Around November 11th, 2025, this object became visible again in Earth's pre-dawn sky after hiding behind the sun for weeks. Not because of magic, because of geometry, because orbits have mathematics. Let's pull apart what happened, what we actually know, and why the hype misses the point entirely. 3I Atlas arrived from interstellar space. Not maybe, not probably. Confirmed. The Atlas Survey Telescope in Rio, Hurtado, Chile, spotted it on July 1st, 2025 at 05:15:11 UTC. 4 exposures across 65 minutes, moving 0.49 degrees per day against stellar background. Observatory code W68. The Minor Planet Center collected 122 observations from 31 observatories within 2 days. Orbital eccentricity 6.144 plus or minus 0.016. That number matters. Anything above 1 means hyperbolic, not bound to the sun, won't return. Perihelion 1.356 astronomical units. Inclination 175 degrees. Hyperbolic velocity at infinity 57.95 kilometers per second. Those aren't estimates. Those are measurements with error bars. Tracing backward using these numbers shows the comet came from the direction of Sagittarius near the galactic center in the southern celestial hemisphere, not from the solar apex in the north like previous interstellar objects. Third confirmed visitor from beyond our system after 1, I Oumuamua in 2017, and 2, I Borisov in 2019. If you value documented astronomical discovery like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual using sources from NASA's Jet Propulsion Laboratory Small Body Database. Browser last updated November 10, 2025, and the Argiv preprint server paper 2507.02757 published. July 3, 2025, by Daryl Seligman and team from Michigan State University, which provides orbital elements confirmed by 122 observations from 31 independent observatories, worldwide within 48 hours of discovery. Now back to the information. Pre-discovery observations pushed the timeline back. Zwicky Transient Facility caught it June 28 and 29, observatory code July 41. More ZTF images from June 14 through 21. Atlas, Chile saw it June 25 through 29. Amateur astronomer Sam Dean found additional Atlas frames from June 5th through 25th. Why no earlier detection? Dense star fields? The comet passed in front of the galactic center. Millions of background stars. Hard to pick out a moving, fuzzy dot. NASA's Transiting Exoplanet Survey satellite had actually recorded it even earlier. May 7th through June 3rd, 2025, when 3I Atlas was 6.4 astronomical units from the sun, already active, already releasing gas, not water. Something else? Something volatile enough to sublimate that far out? Initial reports unclear. Asteroid or comet? Alan Hale saw no cometary features on July 1st, but July 2nd changed everything. Deep random survey in Chile, observatory code X09. Lowell Discovery Telescope in Arizona, code G37. Canada, France, Hawaii Telescope at Mauna Kea, code T14. All 3 showed marginal coma. Potential tail-like elongation, 3 arcseconds angular length. David Jewett and Jane Liu used the Nordic Optical Telescope on July 2nd, confirmed clearly active with diffuse appearance. Miguel Alarcon's team at Instituto de Astrofísica de Canarias used the 2-meter twin telescope at Teide Observatory, same date. Found cometary activity. Multiple telescopes showing reddish coma color indicative of dust. Similar to 2I Borisov's appearance. The Minor Planet Center announced discovery July 2nd. Gave it interstellar designation 3I. Third interstellar object confirmed. Also designated C/2025 N1 Atlas. Non-periodic comet. Size estimates varied wildly at first. Absolute magnitude HV around 12. Assuming asteroid like albedo 0.05 gives nuclear radius around 10 kilometers, but that assumed no coma. Vera Rubin Observatory serendipitously imaged 3I Atlas during science validation June 21 through July 3rd. Showed slight coma diameter increase, provided nucleus diameter constraints. Hubble Space Telescope captured it. July 21st, 2025. Comet was 277 million miles from Earth, revealed teardrop-shaped cocoon of dust. Background stars streaked because Hubble tracked the comet's hyperbolic motion. Continuing observations through August 20th narrowed the size. Nucleus diameter between 0.32 and 5.6 kilometers. Most likely under 1 kilometer. Big range, but improving. Gran Telescopio Canarias high-resolution images showed coma spanning 26,400 by 24,700 kilometers in diameter. About twice Earth's diameter. Not the nucleus, the gas cloud around it. The chemistry surprised everyone. James Webb. Space Telescope observed August 6th, 2025 at 11:02 through 11:20 UTC using NIR spec integral field unit. Heliocentric distance 3.32 astronomical units. Phase angle 16.1 degrees. Total exposure 640 across 4 dither positions. Spectral coverage 0.6 through 5.3 micrometers. Resolving power 30 at 1.2 micrometers up to 300 at 5.3 micrometers. Results announced August 25th. Carbon dioxide dominated coma, not water. Carbon dioxide. Emission at 4.3 micrometers. Water at 2.7 micrometers. Carbon monoxide at 4.7 micrometers. Carbonyl sulfide tentatively detected. Water ice present. Dust scattered light at 1.2 micrometers. The mixing ratio hit 7.6 plus or minus 0.3. Carbon dioxide to water. Among the highest ever observed in any comet. 4.5 sigma above the trend for long period and Jupiter family comets, excluding outlier C/2016 R2. The nucleus was emitting 129 plus or minus 1 kilogram of carbon dioxide per second. 6.6 plus or minus 0.2 kilograms of water per second. 14 plus or minus 0.9 kilograms of carbon monoxide per second. 0.43 plus or minus 0.09 kilograms of carbonyl sulfide per second. Those are measured production rates, not guesses. NASA's SphereX mission observed August 7th through 15th. Detected strong water ice absorption. Extended carbon dioxide coma, agreed with Webb's findings. High carbon dioxide, low water. Neil Gehrels. Swift Observatory detected something unexpected July 31st and August 1st. Hydroxyl radicals. Ultraviolet emission, chemical fingerprint of water broken apart by sunlight. Production rate 1.36 plus or minus 0.35 times 10 to the 27th molecules per second. Surprising, because 3I Atlas was nearly 3 times Earth's distance from Sun. Sunlight usually too weak at that distance for direct surface ice sublimation. Theory emerged. Nucleus, ejecting spray of tiny ice-coated dust grains. Particles smaller than 1 micrometer. Large surface area relative to volume. Faint sunlight heats them efficiently. Icy coatings turn to gas. Creates vast cloud of water vapor away from nucleus. Extended source between 4,000 and 10,000 kilometers from nucleus. Not sublimating directly off surface. Ejected by outgassing of carbon dioxide and carbon monoxide. Very Large Telescope Spectroscopy, August 21st, 2025. Cyanide detected. CN emission, also atomic nickel vapor. Ni in the coma, concentration similar to solar system comets, but the distance wrong. Nickel typically vaporizes close to Sun. 3I Atlas, releasing nickel vapor nearly 4 times Earth's distance from Sun. Temperature too cold for metals to normally vaporize. Rohan Rahat Gaonkar at Instituto de Astrofísica Pontificia Universidad Católica de Chile led the team. Used SOAR telescope. Multiple days of observations. Nickel levels increasing as comet approached soon. Measured using spectrograph and light characteristics. James Clerk, Maxwell Telescope, observed September 7th. Hydrogen cyanide production rate 1.5 plus or minus 0.5 times 10 to the 25th molecules per second. September 14th, the rate climbed. 4.5 plus or minus 1.9 times 10 to the 25th molecules per second. 2 kilograms per second. Cyanide coma. September 15th, about 180,000 kilometers across. Asymmetric. Elongated along antisolar direction. Visible dust tail 50 arc seconds across, about 100,000 kilometers. The comet approached Mars, October 3rd, 2025. Closest approach to red planet, 30 million kilometers, 0.19 astronomical units, 17.6 million miles, 284 million kilometers. ESA's Mars Express and ExoMars trace gas orbiter turned cameras toward it. ExoMars. TGO used color and stereo surface. Imaging system, CASIS, captured series of images October 1st through 7th. Slightly fuzzy white dot moving downward near center. CASIS couldn't distinguish nucleus from coma. 3 I-Atlas too far. Nucleus kilometer wide. Imaging that from 30 million kilometers like seeing mobile phone on moon from Earth. But coma a few thousand kilometers across clearly visible, created as comet approached sun. Heat and radiation bringing it to life, releasing gas and dust, collects as halo surrounding nucleus. Full coma size couldn't be measured. Brightness decreases quickly with distance from nucleus, fades into image noise. Then came perihelion. Closest approach to sun, October 29, 2025, at 11:47 UTC. 1.356 astronomical units, 203 million kilometers, 126 million miles, just inside Mars orbit, between Earth and Mars, eccentricity about 6.1, confirming not gravitationally bound. Third confirmed interstellar visitor after Oumuamua and Borisov. But here's the timing that raises eyebrows. Solar conjunction happened October 21st, 8 days before perihelion. Comet exactly on opposite side of Sun relative to Earth. Impossible to observe from Earth-based telescopes, hidden behind solar glare. Solar elongation, minimum 2.59 degrees, October 21st. When comet, 2.4 astronomical units from Earth. Less than 30 degrees from Sun, October 1st through November 9th. Why does this matter? In astronautics, the optimal point for spacecraft maneuver is closest approach to massive object. Oberth effect. Impulse and direction of peak velocity are opposite, maximizes kinetic energy gain or loss. Most energy efficient for spacecraft engine to burn fuel when orbital velocity greatest. Solar illumination at perihelion delivered over 33 gigawatts of power to surface, assuming minimum diameter 5 kilometers. Was the timing coincidence or design? Earth-based telescopes couldn't see perihelion, but spacecraft could SOHO Solar and Heliospheric Observatory. Stereo A Solar Terrestrial Relations. Observatory launched 2006 orbits slightly faster than Earth. GOES 19. Weather satellite. CCOR-1 coronagraph. LASCO large angle and spectrometric coronagraph. Punch polarimeter to unify the corona and heliosphere. All watched. Images from stereo instruments in GOES 19 and LASCO showed rapid brightening as 3 I-Atlas neared perihelion. Brightness scaled inversely with distance from Sun to power, negative 7.5, plus or minus 1. CCOR-1 resolved glow extending 300,000 kilometers around 3 I-Atlas. Comparable to scale of carbon dioxide plume traced by Spherix August 8th through 12th. Color photometry showed something strange. 3. I-Atlas appeared distinctly bluer than Sun, contrast to earlier observations showing it red, suggesting emission contributed substantial fraction of overall visible brightness. Processing of punch image from October 14th showed compact source. No obvious fragmentation visible. Post-perihelion images. November 5th from 2 sources. R. Naves Observatory in Spain. Virtual telescope project. Both showed compact source of light without clear cometary tail. Fuzzy ball. Sunward direction toward bottom left. No obvious tail. Coma morphology not very different from Hubble appearance. July 21st. This surprised observers. NASA JPL reported non-gravitational acceleration. Parameter A1 normalized at heliocentric value 1 astronomical unit. Based on momentum conservation, the mass fraction lost during perihelion passage, larger than 13%. For typical comet, this should have resulted in massive coma with dust and gas. Solar radiation pressure and solar wind should push material into typical cometary tail pointing away from Sun. No such tail visible. November 5th. Compared to Comet Lemon from Solar System, R. Naves Observatory image November 3rd. Clear cometary tail away from Sun. Expected behavior. 3. I-Atlas different. November 8th. Images by Michael Jaeger, Gerald Raymond, Enrico Prosperi shared on ICQ Comet Observations. Facebook. Complex tail structure. 4 to 5 tails or jets fanning out multiple directions. Commenters noted tails resembled C/2016 R2. Unusual long period comet, extremely rich in carbon monoxide and nitrogen, but poor in dust. November 9th images from Spain by Frank Niebling and Michael Buchner. 2 distinct tails clearly visible, one smoky tail extended upward and right, spanning 30 arc minutes, roughly apparent diameter of full moon. Other anti-tail made of dust particles, 10 arc minutes long, extended downward left towards sun. Inverted time lapse from Leander, United States, November 10th. Celestron Rasa 11-inch telescope. ZWO ASI 2600 MC Pro camera. Each frame 60-second exposure, stacked and inverted in PixInsight, highlighted faint coma and dust tail after perihelion. Photograph. November 7th. Leander, same equipment. Showed diffuse coma and subtle green hue compared to background stars. Now comes the reappearance, November 11th, 2025. Predicted date. 3 I Atlas became visible again in morning sky. Not magic, geometry. Solar elongation increased, comet moving away from sun in sky. Looked low above eastern horizon just before sunrise. Magnitude around 11 to 12, too faint for naked eye, possibly visible in good binoculars under ideal dark sky conditions. Small telescopes show it more reliably. Comet climbing higher each morning as moves away from sun, moving through constellation Virgo, will move into Leo during December. Expected to become dimmer than apparent magnitude 12 through December. ESA's Jupiter Icy Moons Explorer Juice attempted observations. November 4, passed within 64 million kilometers from 3 I Atlas. Best view of perihelion passage, observations using multiple instruments, cameras, spectrometers, particle sensor, coordination with NASA's Europa Clipper considered, twin ultraviolet spectrographs, juice close to sun, using main high gain antenna as heat shield, using smaller medium gain antenna to send data back, much lower rate. Don't expect data from juice observations until February 2026, Europa Clipper predictions, October 30th through November 6th, potentially immersed within ion tail of 3 I Atlas. Opportunity to detect signatures of interstellar comets' ion tail, characteristic changes to solar wind expected. Magnetic draping structure associated with comet may be identifiable. Hera spacecraft, possibly immersed October 25th through November 1st. All these encounters documented, all these measurements recorded. December 19th, 2025. Closest approach to Earth, 1.8 astronomical units, 267 million kilometers, 166 million miles, about twice distance between Earth and Sun. On other side of Sun during closest approach, Webb telescope scheduled for next observations. December, after perihelion, determined composition changes, chart behavior changes, Hubble performing ultraviolet spectroscopy. November, determined composition of gas emissions, sulfur to oxygen ratio, monitor comet on way out. March 16th, 2026. Pass within 0.36 astronomical units of Jupiter, 54 million kilometers, 33 million miles. Juno spacecraft could image it, use radio antenna, check for transmission, technological signature possibility. Age estimates came from Dynamics. Preliminary study, co-authored by Daryl Seligman and Astor Taylor, August 2025. 3 billion to 11 billion years old. Our solar system 4.6 billion years old. If 3I Atlas from thick disk, it could be 7 billion years old. Older than solar system by 3 billion years. Steep trajectory through system indicated origin from Milky Way's thick disk. Ancient region. Much older than thin disk where sun born. Carbon dioxide turns solid to gas, responding to temperature changes much more easily than most elements. Comet likely never been close to another star before brush with sun. Pristine. Ancient. Carrying ices from formation era. Controversy emerged. July 16th, 2025. Astrophysicist Avi Loeb and researchers from Initiative for Interstellar Studies published paper on our curves. Speculated 3. I Atlas could be extraterrestrial spacecraft, anomalous characteristics, apparently large size, lack of identifiable chemicals in early observations, apparently improbable trajectory aligned with solar system's ecliptic plane within 5 degrees. Likelihood 0.2%. During July and August, displayed sunward jet anti-tail. Not optical illusion from geometric perspective, unlike familiar comets. Nucleus about 1,000,000 times more massive than Oumuamua, 1,000 times more massive than Borisov, while moving faster than both. Altogether, likelihood less than 0.1%. Arrival time fine-tuned to bring it within tens of millions of kilometers from Mars, Venus, Jupiter. Unobservable from Earth at perihelion. 8 anomalies total. Loeb scale, rank 4. 0, definitely natural. 10, definitely technological. 4, uncertain. Radio observers asked to monitor. Congresswoman Anna Paulina Luna helping get high-rise images from October 2nd, released to scientific community. If 3, iAtlas maneuvers, releases mini-probes, transmits radio signals, then technological origin confirmed. Other technological signatures include artificial lights, excess heat from engine. If natural comet glued together by weak forces, heating by 770 watts per square meter at perihelion, may break it up. Fragments evaporate more quickly. Resulting fireworks might generate much brighter cometary plume. Most scientists say most likely natural comet. Measurements consistent with comet behavior. High carbon dioxide, not impossible. Just unusual. Alignment with ecliptic, improbable, but not impossible. Size within range of possibility given detection biases. Non-gravitational acceleration explained by outgassing. No radio signals detected. No maneuvering observed. No mini-probes released. Data suggests natural object with unusual composition. Newly commissioned Vera Rubin Observatory, serendipitously imaged, 3I Atlas, June 21st through July 3rd, science validation observations. Showed slight coma diameter increase. Provided nucleus diameter constraints. Would have discovered before Atlas survey if begun observations 2 weeks earlier. Virtual telescope project shared live images, July 3rd, live stream. Bruno Guillet captured images with Unistellar Smart Telescope. Frank Marcus, senior astronomer SETI. Institute Chief Scientific Officer Unistellar said caught early enough to coordinate observation campaigns with Citizen Science Network. International collaboration, professional observatories, amateur astronomers, space telescopes, Mars orbiters, all watching, all measuring, all recording data, discovery implications calculated. Spatial number density 10 to the negative 3 per cubic astronomical unit for objects with radii greater than or equal to 3 I Atlas. Means interstellar objects this size or larger, relatively common in galaxy. About 1 per 1,000 cubic astronomical units of space. Detection rate limited by survey capability. Brighter, more active objects easier to spot. Atlas survey designed for near-Earth asteroid detection. Catches interstellar visitors as byproduct. ZTF scans northern sky. Multiple surveys operating. More discoveries expected. Each interstellar object teaches us about planet formation around other stars. Each one data point. Each one glimpse into distant stellar nursery. Comets are remnants. Leftovers from system formation. Pristine samples. Time capsules. 3. iAtlas carries material from formation of planetary system around distant star. System that formed billions of years ago. Star we can't identify. System we can't observe directly. But comet came to us, brought samples. Free delivery from across galaxy. Comparison to previous visitors matters. Oumuamua. First detected October 19, 2017. Pan-STARRS Telescope, Hawaii. Tumbling elongated object, no coma, no tail, inert, asteroid-like but hyperbolic orbit, accelerated away from sun, non-gravitational. No outgassing detected. Hypothesis ranged from a nitrogen iceberg to hydrogen iceberg to light sail, length 230 to 420 meters depending on assumptions. Left system before detailed characterization possible. Borisov. Discovered August 30, 2019. Gennady Borisov using Margot Observatory Crimea. Clear comet, active, tail visible, coma obvious. Spectroscopy showed cyanide carbon monoxide water, dust to gas ratio. Nucleus radius 200 to 500 meters. Color reddish, similar to solar system comets, fragmented near perihelion. Nucleus split, behaved like typical comet just from another system. 3 iAtlas, different from both. Larger than Borisov, more active than Oumuamua. Carbon dioxide, rich, unlike typical comets. No clear tail immediately post-perihelion, unlike expected behavior. Complex jet structure. Nickel emission at cold temperatures. Multiple anomalies. Still natural. If you value documented astronomical measurement, like this, subscribe. It's the best way to support our work. Comment from which city you're hearing this from. This script researched and factual using sources from the Astrophysical Journal Letters, volume 991, article L, 43, published September 26, 2025 by Martin Cordner and team from NASA Goddard. Space Flight Center reporting JWST and IR spec. Observations with spectral coverage, 0.6 through 5.3 micrometers, revealing carbon dioxide to water, Mixing ratio 7.6, plus or minus 0.3 at heliocentric distance, 3.32 astronomical units. An ARGF preprint 251, 0.18209. Reporting production rates of 129 plus or minus 1 kilogram per second carbon dioxide at August 6th observation. Now back to the information. Historical context matters. Edmund Halley, 1656 through 1742. Calculated comet's return, proved same comet appearing periodically. Comet named after him returns every 75 to 79 years. Last appeared 1986, next appearance 2061. Halley's work established comet's orbit sun, not atmospheric phenomena, not omens. Celestial mechanics. Jan Oort, 1900 through 1992. Proposed cloud of comets surrounding solar system. Oort cloud, reservoir of trillions of icy bodies. Extends 50,000 to 200,000 astronomical units from sun, quarter to halfway to nearest star. Long-period comets originate there. Gravitational perturbations send them sunward. Take millions of years to orbit. But Oort cloud belongs to sun. Gravitationally bound. 3 I Atlas, not from there. Every star probably has equivalent cloud of comets around it. Occasionally, gravitational kick sends one into interstellar space. Travels for millions or billions of years. Crosses paths with another star system. Detected if passes close enough. 3 I Atlas made that journey. Unknown origin star. Unknown original system. Now measured, documented, characterized by dozens of Earth observatories and space telescopes. Light curve data, refined understanding. Spin period 16.16, plus or minus 0.01 hours. Amplitude approximately 0.3 magnitudes. Rotation consistent with active comets. Nucleus rotating, not tumbling chaotically. Stable spin. Observations. July 2nd through 29th by ground-based telescopes. Multiple sites. Photometry showing periodic variation. 17 observatories contributed timing data, fit to Fourier series. Primary frequency, 0.0618 cycles per hour, 16.16 hour period. Secondary features, suggesting either elongated nucleus or surface albedo variations. Shape possibly ellipsoidal. Axis ratio, maybe 1.3 to 1. Consistent with rotating ellipsoid. Not unusual for comet nucleus. Dust measurements came from multiple sources. Grand Telescopio Canarius images showed dust production. Estimated 12 to 120 kilograms per second. Range wide because scattering properties uncertain. Albedo unknown. Grain size distribution unknown, but order of magnitude correct. Hubble images showed teardrop shape. Dust accelerating away from nucleus. Solar radiation pressure. Particles micrometer size to millimeter size. Smaller particles accelerate faster. Larger particles remain near nucleus longer. Distribution creates teardrop morphology. Tail would form if enough small dust. 3 I Atlas produced complex jets instead. Multiple emission directions. Not simple sunward, anti-sunward. Active regions on nucleus. Rotating nucleus brings different regions into sunlight. Creates jet pattern. Observed November 8th with 4 to 5 distinct structures. Trajectory calculations precise. Inbound velocity 61 kilometers per second at large distance. Approached from southern sky. Came up through ecliptic plane at steep angle. 175 degree inclination means retrograde, moving opposite to planets. Closest to Mars, October 3rd. Closest to Sun, October 29th. Closest to Venus, November 3rd. Closest to Earth, December 19th. Closest to Jupiter, March 16th, 2026. Then leaving. Outbound velocity also 61 kilometers per second at large distance. Hyperbolic excess velocity. Won't slow to zero, won't turn around. One-time pass, never returning. Exit direction approximately toward constellation of southern sky. Back to interstellar space. Next star encounter. Who knows? Millions of years, billions of years. We'll travel until perturbed by galactic tide, or close past to another star, or absorbed by molecular cloud, or survives until galaxy ends. Detection statistics inform probability. Atlas survey operates 4 telescopes. Chile, Hawaii, South Africa, Mauna, Loa. Each telescope surveys sky repeatedly, catches moving objects, asteroids, comets, reports to Minor Planet Center. Center determines orbits, distinguishes bound from unbound. 3 surveys worldwide capable of detecting interstellar objects. Atlas, Pan-STARRS, ZTF, maybe Rubin soon, sky coverage partial, many blind spots. Many objects pass undetected. 3 confirmed in 8 years. Oumuamua 2017, Borisov 2019, 3i Atlas 2025. Rate approximately 1 every 2 to 3 years, but detection rate, not actual rate much higher. Detection bias toward close passes, bright objects, large objects, active objects, faint small inactive objects pass unnoticed. True rate probably 10 to 100 interstellar objects passing through inner solar system per year. Most never detected. We catch brightest, largest, most active, closest. Formation scenarios discussed. Planetary system formation produces billions of comets. Outer regions, a protoplanetary disk. Beyond ice line, water freezes. Carbon monoxide freezes, carbon dioxide freezes, material accumulates, forms comet nuclei. Planetary formation scatters many. Giant planet migration kicks billions into interstellar space. Every planetary system ejects comets. Galaxy full of orphan comets, drifting between stars. Occasionally one enters another system. We detect it, sample it, learn about distant planet formation. 3. I-Atlas composition suggests formation beyond carbon dioxide ice line. Region where carbon dioxide freezes solid. Temperature below 170 Kelvin. Pressure typical of protoplanetary disk. Distance from star depends on star luminosity. Solar-type star has carbon dioxide ice line around 20 to 30 astronomical units. Dimmer star closer, brighter star farther. We don't know parent star. Can't calculate exact formation location, but composition constrains it. Rich in carbon dioxide implies formation, cold region. Low water content implies either carbon dioxide-dominated formation environment or subsequent processing. Radiation exposure, cosmic rays, galactic cosmic rays over billions of years. Can alter surface composition, deplete volatile elements, crystallize amorphous ice, change isotope ratios. 3. I-Atlas, old enough for significant radiation exposure. 7 billion years drifting interstellar medium means radiation dose massive. Isotope measurements attempted. JWST spectrum showed heavy carbon dioxide. Carbon-13. Ratio of carbon-13 to carbon-12 important. Solar system comets show ratio around 1 to 89. Interstellar medium varies. Molecular clouds different. Stellar ejecta different. Supernova products different. 3. I-Atlas ratio uncertain. Partial obscuration by dust and other gases made quantification difficult. Preliminary analysis suggested consistent with galactic average, not definitively measured. Future observations may clarify. December JWST observations. Higher signal to noise, better baseline subtraction. May resolve isotope question. Sulfur isotopes also interesting. Sulfur 32 to sulfur 34 ratio. Oxygen isotopes, oxygen 16 to oxygen 18. Each isotope ratio constrains formation environment, temperature, pressure, chemical processes, inherited from molecular cloud or processed in protoplanetary disk. Measurements difficult, requires high spectral resolution. Bright emission lines, long exposures. 3i Atlas, faint magnitude, 11 to 12, challenging target, ongoing monitoring, data accumulating, comparison to solar system analogs. Useful, C/2016R, 2 pan-stars. Mentioned earlier, exceptionally carbon monoxide rich, carbon monoxide to water ratio over 100, formed an outer solar system, possibly Oort cloud object, visible from 2016 through 2018. Showed blue gas coma, rich in nitrogen and carbon monoxide, poor in dust. 3. I-Atlas resembles R2 in some ways. High volatile to water ratio, complex tail structure, different parent molecule, carbon dioxide instead of carbon monoxide, but similar physics. Volatile driven activity, low dust production, unusual composition makes them outliers among comets. Most comets water rich. Ice sublimates near sun, creates classic dust tail, gas tail, smooth coma. Predictable behavior. 3. I-Atlas and R, 2 different. Volatile rich, active far from sun, carbon-bearing ices dominating, possibly formed same type of environment. Cold outer regions of disk, beyond nitrogen ice line, beyond carbon monoxide ice line, pristine primitive material. Technology hypothesis addressed directly. Loeb proposed 8 anomalies, 1 trajectory aligned within 5 degrees of ecliptic, probability 0.2%. Improbable, not impossible. Random interstellar object could by chance align with ecliptic. Dice roll, 2 sunward jet antitail July-August. Appears to point toward sun. Most comets show tails pointing away. Sunward features result from dust grain orbital dynamics. Particles released move in slightly different orbits. Some appear sunward from viewing geometry. not unique to 3I Atlas, observed in other comets. 3 nucleus million times more massive than Oumuamua, 1,000 times more massive than Borisov. Size range: Oumuamua, small, maybe 200 meters. Borisov, medium, maybe 500 meters. 3I Atlas, large, maybe 1 to 5 kilometers. Detection biases favor larger objects. We detect bright ones, miss dim ones. Sequence: Oumuamua, Borisov. 3I Atlas, consistent with size distribution. Next detection might be smaller, might be larger. Statistics of 3 insufficient. 4 arrival time brought it close to Mars, Venus, Jupiter, hidden from Earth at perihelion. Suspicious timing, but orbital mechanics, deterministic. We calculate positions. 3I Atlas didn't choose arrival date. Arrived when physics dictated. Perihelion date set by orbital energy and angular momentum. Conjunction with Earth coincidental. 5 non-gravitational acceleration detected. Explained by outgassing. Carbon dioxide sublimates. Momentum transfer. Pushes comet. Jet force. Measurable. Calculated. 13% mass loss consistent with observed brightness and gas production rates. 6. No clear tail post-perihelion. November 5th. Explained by viewing geometry and low dust. Complex jets observed November 8th. Tails visible November 9th. Developed as expected, just delayed. 7 rapid brightening near perihelion blue color, explained by emission from gases. Fluorescence. Sunlight excites molecules, re-emit at specific wavelengths, creates blue glow, different from reflected sunlight. Natural phenomenon. 8 high nickel emission far from sun, unusual but observed. Nickel-bearing minerals sublime at cold temperatures under some conditions, possibly ammonia-nickel complexes, or nickel carbonyls. Carbonyl sulfide detected. Nickel carbonyl. NiCO4 sublimates 97 Kelvin. Cold enough? Mechanism exists. Conclusion requires data, not speculation. 3I Atlas interstellar object confirmed. Measurements precise. Composition unusual. Carbon dioxide rich. Water poor. Age billions of years. Origin unknown. Distant star. Passing through solar system one time. Visible November 11th. Morning sky after perihelion reemergence. Magnitude 11 to 12. Telescope required. Moving through Virgo toward Leo. Approaching Earth. December 19th. Closest approach. 166 million miles. Safe distance. Passing Jupiter March 2026. Then leaving forever. Observing campaign continuing. Hubble monitoring. Webb observing December. Ground telescopes tracking. Data accumulating. Every measurement refines understanding. Every spectrum constrains composition. Every image maps structure, not mystery. Science, not hype. Measurements, not alien spacecraft. Ancient comet from distant planetary system delivering free samples of distant planet formation billions of years ago. Teaching us about galaxy, showing us chemistry possible around other stars, proving interstellar visitors common. Demonstrating universe connected. Matter exchanges. Systems interact. Comets cross between stars. We witness it, we measure it, we learn from it. 3I Atlas represented opportunity. Rare event. Interstellar visitor. Approaching sun. Becoming active. Releasing gases. Fragmenting maybe. Surviving maybe. Scientists mobilized. Telescope time allocated. Spacecraft retargeted. International collaboration. Dozens of observatories. Hundreds of researchers. Thousands of images. Spectra. Measurements. Coordinated campaign. Share data openly. Archive preprints. Published papers. Results available. Anyone can read. Anyone can verify. Reproducible science. Peer review. Error bars reported. Uncertainties acknowledged. Competing hypotheses evaluated. Evidence weighted. Conclusions drawn carefully. Not definitive. Probabilistic. Best explanation. Given data. Subject to revision. Given new data. How science works. November 11th, 2025 sits in timeline. Pre-discovery, May 7th. Discovery, July 1st. Confirmation, July 2nd. Hubble imaging, July 21st. JWST observation, August 6th. Results, August 25th. Mars approach, October 3rd. Solar conjunction, October 21st. Perihelion, October 29th. Reemergence, November 11th. Closest Earth approach, December 19th, 2025. Jupiter approach, March 16th, 2026. Each date documented, each event measured, timeline complete. Archive preserved, future researchers access. 100 years from now, someone will study. 3-eye atlas. Read these papers. View these images. Analyze this data. Compare to later discoveries. Statistical sample growing. Understanding improving. First 3 just beginning. Next 3 may clarify. First 10 established trends. First 100 defined populations. Each interstellar visitor teaches us. 3-eye atlas taught us carbon dioxide. Rich comets exist. Taught us old objects survive billions of years. Taught us interstellar space not empty. Full of wanderers, full of travelers, full of stories. Final observation requires perspective. We live in era of discovery, era of measurement, era of understanding. Telescopes scanning sky, surveys operating continuously, detection capability improving. Rubin Observatory beginning operations. 40 times sky coverage of current surveys, detect maybe 10 interstellar objects per year, characterize them, measure them, build catalog, understand populations. Within decade, we'll know commonality. Within century, we'll have visited 1, sent spacecraft, rendezvous mission, sample return mission, touch interstellar material, bring it to lab, analyze isotopes, determine formation conditions, identify parent star, connect visitor to origin, close loop. 3-eye atlas just beginning, first of many, each one glimpse into galactic ecosystem, each one connection point, each one reminder we're part of something larger, not isolated, not alone, not unique, part of galaxy, part of process, part of story spanning billions of years and light years. 3-eye atlas came to us, traveled billions of years, crossed light years, entered our system, passed our sun. Visible our morning sky, November 11th, small dot requiring telescope, faint smudge of light, ancient traveler, cosmic messenger, scientific treasure, teaching us, showing us, reminding us, universe vast, connections real. Knowledge growing, questions answering, one measurement at a time, one spectrum at a time, one visitor at a time. The comet left traces, data in archives, images in databases, spectra in repositories, papers in journals. Knowledge in minds, changed our understanding, shifted our perspective, expanded our view, not because of hype, because of facts, not because of speculation, because of measurements, not because of mystery, because of science. 3-eye atlas morning sky return around November 11th explained without hype. Geometry brought it back. Telescopes found it. Researchers measured it. We learned from it. Simple as that. Complicated as that. Beautiful as that.